All right, so let's look at number 11. All right. Oh, I love this one. You're testing a new amusement park roller coaster with an empty car of mass 120 kilograms. Okay, so let's just draw it. Okay, so you got the little car here, the roller coaster car. And of course it's going to be up here when it's at the top of the loop. All right. All right, and this is point A, and this is point B. Okay. And one part of the track is a vertical loop with a radius of 12 meters, so the radius of the loop is 12 meters. All right. All right. At the bottom of the loop, point A, I label it, the car has a speed of 25 meters per second. And at the top of the loop, point B, it has a speed of, and we could say VA and VB. Okay. No, it's not a big deal. A is initial, B is final. Okay. B comes after A. Come on. Use some reasoning, okay? All right. And it's 8 meters per second. Okay. All right. As the car rolls, let's see, as the car rolls from point A to point B, how much work is done by friction? So we want to know the work done by friction. Question mark. Let me ask you something. What kind of, now remember, we looked at our conservation of energy equations, and we had two, didn't we? We had this one, U initial plus U final. Stop doing that. Okay. K initial is equal to what? K final plus U final. But that is when what? Only gravity, right, is operating on the system. Only gravity. What about when you have other work involved? Well, it was U initial, it was work other, plus U initial plus K initial is equal to K final or U final. It doesn't matter which one you put first, doesn't matter. Because they're both positive, doesn't matter. All right? Okay? Well, let me ask you something. Is friction an other work? Most certainly is. Okay? All right, now, let's do some more analyzing here. Okay, I think it's pretty obvious we have an initial velocity and a final velocity, so we know Ki and Kf's not going anywhere, right? Well, let me ask you something. What about potential energy? Is this going to be a conservation of energy equation? Yeah, because you've got potential, you've got kinetic, and you have other work called friction. So we're going to use that equation, aren't we? We have to. All right, what is the potential energy? What is U initial right here at A? All right, now that's on the ground. We're assuming that ground level's right there. It's 0, isn't it? 0 joules, orange juice, all right? All right, so do we have, it's going to be max right here, isn't it? It's going to be maximum, right? We're going to have maximum potential energy at the top of the loop, right? At the top. Okay, all right, good. Okay. All right, so what happens to our U initial term? It's gone. Now our equation becomes what? Work other, which is friction, plus what? Ki, that's capital K, is equal to K final plus U final. And we want to find what? Work other. So work other, which is friction, let me write over here. So work other is equal to, you got to subtract Ki from both sides, so it becomes K final plus U final minus Ki, or you could have said K final minus K initial. It doesn't matter. It's still negative. I got it in there. Okay? Now, y'all, all we do is work it. Okay? So just plug everything in. So you got work other, which is friction. K final, we got what? 1/2. The mass was, oh shoot, I didn't write the mass down, did I? The mass of the car was what, 120? Yes. Thanks. All right, so we got 120 kilograms times what? 8 squared plus, all right, we've got the mass of the car was 120 times gravity times, what distance am I going to use? The radius was 12, so from the top all the way down is what? 24 meters. Minus 1/2 times 120 times 25. Is that right? Yeah. Is that right? Yeah. And so we get work other. It works out beautifully. Negative. I put it in scientific notation, 5.44 times 10 to the third joules, but it's negative work. Now, if you take this and look, if you want to check yourself, this is how you could do it. You could turn it around, drop out the final velocity and solve it for final velocity, and plug this in as negative and plug potential energy in as negative, and you should get 8 meters per second for your final velocity. So that's a good way to check yourself. Did you hear what I just did? Solve it for final velocity. Okay? So move everything over here. Okay? And you solve it for final velocity, and you'll see that it should come out to be 8 meters per second. 7.99, something like that. Okay? Okay? Question, yes? Yeah. Yes. No. Because it's just wanting to know from here to here, not all the way back around. Well, technically, in other words, you're saying pi radians, okay, for the distance. Yeah. You do go through the arc, and that would affect it a little bit. Yeah, it would affect it a little bit. So the circumference would be what? See, it's pi r squared. Pi times diameter is circumference, so pi r squared. Does that sound right? Yeah. So it'd be pi times diameter would be what? So pi times 24. So that's 73 divided by 2. 37 point. Yeah. Well, okay, that's along the arc. Okay. But you got to remember, potential energy is what? Height above the ground, above the surface. So the arc's really not going to affect it that much. You see what I'm saying? It's really not going to have that much of an effect on it, because we're looking at potential energy. And potential energy is affected by height above the ground. Okay? Because now if it was at an angle, if we wanted to know how much friction would it be right here, then yeah, we would have to look at that. We'd have to find an angle. We'd have to plug an angle in there. But we're looking at what? We're actually looking the x direction. I know that's up and down is not x, but remember, y'all were talking about work. It'd be a cosine of 0, so it'd be maximum, because we're just looking at the effect of gravity from here to here. Okay? Okay, that's a good thought. Okay. All right. Any other questions? All right, did somebody say number 5? Number 5. All right. Okay. All right, we have a baseball. All right, let me write this on here too. And 5. Okay. All right, so we got a baseball thrown from a building. All right, and we'll just do that right there. All right. Okay, so it's thrown from a building, from the roof of a 22-meter tall building. So the height of the building, y, is equal to 22 meters. Okay. All right. The initial magnitude is is 12 meters per second. Actually, I didn't put no arc on it, did I? Let's do that. All right, so he's throwing it at an arc, and then it comes down here like that, something like that, okay? And so this angle right here is 53.1 degrees, is that right? Yeah. All right. And the velocity, now this is just initial velocity. It's not y, it's not x. It's just initial velocity. It's 12 meters per second. And it's directed at an angle of 53.1 above the horizontal. What is the speed of the ball just before it strikes the ground? Okay. So we want to find the speed of the ball just before it strikes the ground. Okay. And it says to do what? It says, what is the speed of the ball just before it strikes? Use energy methods and ignore air resistance. Okay. Use energy methods and ignore air resistance. Okay. So, remember, the x directional velocity is what? It's constant, isn't it? The y is the only one that's being affected here by gravity, right? So, we know that the change in kinetic energy is equal to what? It's equal to U, isn't it? Right? Okay. All right, so we got mgy is equal to 1/2 mv squared final minus 1/2 mv squared initial. And we want to find the final velocity, don't we? And that's going to be, our equation is going to look like what? The square root of 2 gy plus v final. Or excuse me, v initial. My bad. Yeah, the initial, my bad. Okay, now notice something here. We're only concerned about the initial velocity, okay? Or excuse me, yeah, the initial and final velocity. All right, so let's work it now. It's 2 times 9.8 times 22 plus, oh, for crying out loud, I can't think, 12 squared. Okay. And you should get this, 23.9 meters per second. Okay. All right. Okay. And that's just before it hits the ground. All right. Now that's A. What about B? All right. It says, what is the answer of part A if the initial velocity is at an angle of 53.1 degrees below the horizontal? And now this is a little tricky. They're assuming we've already taken the sine. Okay, now that's probably what's confusing some of you. That we you're throwing it up at an angle, so you should actually, you should have your initial velocity should be sine of that, right? Because it's at an angle. Because what do we know about the velocity in the x direction? It's constant. We're not concerned about the x direction. All we're concerned about is the y direction. So they should have worded this a little differently. It should be the sine of that, okay? All right. They should have said this is the angle in the y direction is what I'm saying. They should have said that, but they didn't say that, okay? All right, so we get 23.9, 23.9 or 24 meters per second. Now, what about part B? Does it matter throwing it down? Because look, remember what I said a minute ago. Remember I told you, when you throw an object, once it leaves your hand, the only thing that's affecting it is what? We know air resistance, but we're negating air resistance here because it tells us to. The only thing it's affecting it is what? Gravity. Okay? That's the only. So if I throw it down, is that going to affect it any? Because again, once it comes out of my hand, doesn't matter whether I'm throwing it down or whether I'm throwing it up at an angle or down. It's not going to affect the final velocity. It's not going to affect the final velocity. Because remember, once it's out of your hand, the only influence on it is gravity. Okay? All right. So it's the same. It's the same. I know that's hard to believe, but it really is. Because remember, y'all, you've got to think about what is affecting the projectile. Is the gravity any different up as opposed to down? No. Okay? No. It's still falling the same distance, 22 meters. Okay? It's still falling the same distance. All right?
So what are we supposed to do 12 squared sine into 3.1 in that first equation?
Well, the way it's worded, you should have if because the reason I did it this way, this don't match. If you do it that way, it won't match the answer in the book. So I'm assuming that's what I was saying. They went ahead and did that. So if the question's a little off, I don't know why they gave you the angle. They should have said that's the y velocity. Okay, so it's a little bit confusing. Okay, because if you go on and take the sine of that, it's going to come out a different answer. Right? Because you're going to get, what's the sine of 53.1 and 12 times 12? It's, yeah, it's a whole lot less, isn't it? Okay. So I wouldn't do that to you. I would just say, look, you throw it off the building, here's the initial velocity, you throw it horizontally. I'd say you throw it horizontally off the building like that. Okay, at 12 meters per second. That's really what they should have said. So I wouldn't do that to you. Because if you work it the other way, you're not going to get that answer. And that's what's in the back of the book. Because when I saw that, I thought, oh, crap. Okay. Okay? So if I were to give you that problem, I'd say threw it horizontally off the building. Okay? All right. And that's the way they should have worded it. All right. Now, what about part C? If the effects of air resistance are included, will part A or B give a higher speed? Okay, does gravity change? Nope. But what will happen to how far out it travels? It decreases, right? Because you've got drag force. So if I throw it like that or this or down, it doesn't matter. You've got air resistance, and so instead of it going here, it's going to come out here. You got drag. You got air resistance. Okay, so it doesn't go as far. So it doesn't affect gravity. Shouldn't affect the speed, it just won't go as far. Okay, like I said, y'all, some of these questions are not worded. This is one they didn't word it right. Okay, because when you work it out, they didn't take into consideration the sign. Okay, And they put that answer in the back of the book, and I know if you work it, and I told you, when you throw it at an angle, you have to find the y velocity, which you sine, and that's exactly right. But they didn't work it that way. They didn't put the solution that way. So they worded it wrong. They should have said throwing it horizontally. And if I were to give you one like that, you're not going to have this one on the test, but if I were to give it to you like that, I'd say throw it horizontally. Okay, off a building. All right. Okay. All right.